Swayam Prabha. Digital India. Educated India.
Now we are going to discuss how to solve a numerical example related to the Neuro-Fuzzy system Mamdani approach. The statement of the problem is as follows. So, here we are going to develop one Neuro-Fuzzy system based on the Mamdani approach, and this particular fuzzy reasoning tool is represented using the structure of a multi-layered the network. There are two inputs I 1 and I 2, and there is only one output, that is O of the fuzzy logic controller. The neural network consists of 5 layers as we discussed, and the function of each layer is indicated in the figure. The figure I am going to show you. The input I 1 has been expressed using the linguistic term like near, far, very far. So, there are 3 linguistic terms, near, far and very far. Now, similarly, the 3 other linguistic terms like your small, medium and large have been utilized to represent the second input, that is your I 2, and the output has been represented using 3 other linguistic terms like your low, medium, low, high and very high, that is LW, H and your the VH. Now, I am just going to show you. So, this particular the network, the membership function distribution of the inputs and the outputs are assumed to be triangular in nature, and here the base width of near, very far and half base width of far triangle are kept equal to V 11, then comes your V 13 and 12 respectively for the first input, that is I 1. Similarly, for I 2, so your this V 24, V 26, V 25 are used to represent the base width of small, large and half base width of your the medium triangles. Now, your this W 11, W 31 and W 21 indicate the base width of triangles representing low and very high outputs and half base width of your the high triangle. Now, here actually the starting values for this I 1, I 2 and this output are assumed to be equal to 1.0, 10.0 and 5.0. I am just going to show you that the figure. Now, we will have to find out the deviation in prediction for the training scenario, which is nothing but I 1 equals to 1.6, I 2 equals to 18.0 and the output is nothing but is your 9.0. So, for this particular training scenario, so I will have to find out what should be your the deviation in prediction. Now, let us see how to determine so that particular the deviation in prediction. Now, this shows actually the Neuro-Fuzzy system. Now, here let me explain. So, I have got 2 inputs here, one is I 1, I 2 and as usual on this layer 1 we use the linear transfer function. Now, on layer 2 actually we try to represent the connecting weights between your the first neuron lying on the input layer and the first neuron lying on the second layer. So, that is nothing but is your say V 11, then comes V 12, V 13. Now, V 11 is going to represent near, V 12 is going to represent your half base width for the far and VFR, your V13 is going to represent your the base width for very far right angle triangle. Similarly, your the membership function distribution for the linguistic terms used to represent I2 are actually denoted by V24, then comes V25, then comes your V26. Now, there are 3 linguistic terms for I1, 3 other linguistic terms for I2. So, here I have got actually the 9 rules, and this is nothing but the layer 3, that is the AND operation layer, and the layer 4 is nothing but the fuzzy inference, and layer 5 is the defuzzification. Now, the connecting words, that is your W11, W11, then comes your W21, and this is nothing but W31, are going to represent either the half base width or the base width of your the triangular membership function distribution used to represent the output variable. Now, let us see how to find out the deviation in prediction. So, for this particular the training scenario. Now, as we discussed previously, so here you can find out that V11 is kept equal to V12 and that is kept equal to V13 just to ensure the symmetrical triangular membership function distribution for I1. Then V24, V25 and V26 are nothing but are going to represent the symmetrical membership function distribution to represent I2. Then comes your W11 equals to W21 equals to W31 are used to represent the triangular membership function distribution for this the output, and we consider the symmetrical membership function distribution. Now, here we assume the numerical values for, so this particular V, that is V11 equals to V12 equals to V13 and that is kept equal to 0.3. Then V24 equals to V25 equals to V26, that is kept equal to 0.6. Then W11 is equals to W21 is equals to W31, that is kept equals to your 0.4. And you can see that, so all such values are in the normalized scale lying between 0 and 1. Now, here the range for this B1, B2 and B3. Now, this B1 is going to represent what should be the half base width or base width of the triangular membership function distribution used to represent I1. B2 is the half base width or the base width of the triangular membership function distribution used to represent I2, and B3 is nothing but it is going to represent either half base width or base width of the triangular membership function distribution used to represent the output. And we are going to use actually the center of sums method for defuzzification. Now, here one thing I should mention, that although these values, the V, V and W values are in normalized scale, so you will have to find out the real scale values corresponding to these particular the normalized value, and considering the ranges for your the different variables like your B1, B2 and B3. Now, B1, B2, B3 are having different ranges, and we will have to use this normalized value to find out what should be the actual real values for this B1, B2 and B3. Now, this I am going to discuss in details now. Now, this shows actually the manually constructed membership function distribution for this I1, I2 and your the output, and as I told that for this particular I1 there are 3 linguistic terms, near, far and very far, and we are considering the triangular membership function distribution. Now, this is actually one right angle triangle, here also we consider one right angle triangle, and this is nothing but the isosceles triangle, and this B1 is going to represent the base width of this triangular right angle triangle or the half base width of this isosceles triangle. Similarly, to represent I2, we use three other linguistic terms, that is your small, medium and large, and the B2 is used to represent the half base width of this isosceles triangle or the base width of this particular the right angle triangle. Now, similarly, to represent the output O, we use three linguistic terms, that is your low, medium and very high, low, high and very high, and B3 represents either the half base width of this isosceles triangle or the base width of this particular the right angle triangle. And for simplicity, we are considering the symmetrical membership function distribution. Now, as I told that corresponding to this normalized value of your the connecting weight, so you will have to find out the real values. How to find out the real values? Now, to find out the real values, so we use this particular the equation, that is x real value is nothing but n is nothing but the normalized value multiplied by x max minus x min plus x min. Now, for a particular variable say B1, if I know the normalized value, that is nothing but 0.3, if I know the maximum value for B1, that is 1.5, and the minimum value for this particular your B1, that is 0.5. So, very easily I can find out what is the real value for this particular the B1. So, the real value for this B1 is found to be equal to 0.8. Similarly, we can find out the real value for this particular B2, and B2 is nothing but the normalized value of 0.6 multiplied by, so B2 maximum is 15.0, B2 minimum is 5.0 plus B2 minimum is 5.0. So, this is nothing but 11.0. Similarly, for this B3 we can find out the real value. So, n is the normalized value is 0.4, B3 maximum is 8.0, B3 minimum is 2.0 and B3 minimum is 2.0, and if we substitute we will be getting that is 4.4. So, the real value for B1 is 0.8, B2 is 11.0 and B3 is nothing but 4.4. Now, using these real values, actually we can modify the membership function distribution now. So, the modified membership function distribution will look like this. So, the starting value for I1 that has been kept constant to 1.0, but this particular B1 has been changed. Now, similarly, I will be getting this modified membership function distribution for I1. Similarly, we get the modified membership function distribution for I2, and we also get the modified membership function distribution for your the output. And once you have got the modified membership function distribution, now if I just pass a particular value of I1 input, another value of this particular say I2. Now, corresponding to this particular I1, so I will be getting actually the two mu values, one is corresponding to the near, another is corresponding to your far. Similarly, corresponding to this particular value of I2, so I will be getting so a particular mu value corresponding to small, another mu value corresponding to this particular the medium. So, here there are two mu values, here there are two mu values. So, 2 multiplied by 2, so there is a maximum 4 fired rules, and using that particular fired rules, so we will have to find out what should be the fuzzified output, and then we will have to go for your the crisp output using defuzzification. Now, this table shows actually those 9 rules. The rules are as follows. So, if I1 is near and I2 is small, then the output is low and so on. So, here we have got 9 rules, and as we discussed that out of these 9 rules only 4 are going to be fired. Now, whatever I discussed little bit, so we have written it here. So, let us try to see. So, you can see that on layer 1 we consider the linear transfer function. So, the inputs were actually I1 was 1.6, I2 was 18.0. So, 1 I1 is nothing but I1 is 1.6, then 1 I2 is nothing but I2 is 18.0, and as we consider linear transfer function on the first layer. So, output is equals to input. So, 1 O1 is nothing but 1 I1 is 1.6, then comes your 1 O2 is equals to 1 I2 is nothing but 18.0. Now, here once you got this particular the output, now actually what we do is we try to find out what should be the mu value. Now, I1 is nothing but 1.6 and I2 was 18.0. So, corresponding to this 1.6, now if I just draw it here 1.6, now if I draw 1.6 here, then we can see that it could be near or it could be far. So, there are two possibilities. So, corresponding to this particular I1, so I1 can be called either near or far. Now, it can be called near with some membership function value, that is 0.25, and it can also be called far with another membership function value 0.75. Now, for this triangular membership function distribution, how to find out this mu value using the principle of similar triangle. So, that thing we have discussed in much more details. So, I am not going for that once again. So, corresponding to I1, the two mu values we can find out. Similarly, corresponding to your I2, so this I2 can be called either small or medium, and we can find out mu small is 0.272727 and mu medium is nothing but is your 0.727272. So, we can find out your the mu values, that is the membership function values. That means your the fuzzification is over. Now, once you have done this particular fuzzification, now we go to layer 3. Now, as I told that on layer 3 we have got 3 multiplied by 3, 9 combination or the 9 possible rules, and out of 9 in fact only 4 rules are going to be fired. The 4 fired rules are as follows. If I1 is near and I2 is small, then the output is something that I have not written it here. The second fired rule, if I1 is near and I2 is medium, then the output is something. The third fired rule, if I1 is far and I2 is small, then the output is something. Then if I1 is far and I2 is medium, then the output is something. So, there are 4 fired rules. So, out of 9, 4 rules are going to be fired. Now, corresponding to these fired rules, actually we will have to find out what should be the output. Now, if you see the inputs of the third layer, so that is nothing but your the 2 mu values corresponding to the first fired rule. So, 3 I1 is nothing but, so the 2 mu values, that is 0.25 and 0.272727, then 3 I2 is 0.25 and 0.727272, then 3 I4 is 0.75 and 0.272727, and 3 I5 is 0.75 and 0.727272. Now, we compare. So, we try to find out what should be the output of the AND operation layer. So, 301, that is the output, that is nothing but the minimum between these two, and this will be the minimum. Then 302 is the minimum between these two, and this will be the output, and 304 is the minimum between these two. So, this is the output, and 305 is the minimum between these two, and this is actually your the output. So, we try to find out the minimum of the two mu values, and once you have got this, now we are in a position to know the output of your the third layer. Now, we go for your the fuzzy inference, and that is nothing but layer 4. Now, in the layer 4, corresponding to each of these particular input combination, the fired input combination. So, we know this particular output. For example, say the first fired rule is if I 1 is near and I 2 is small, then the output is low. Similarly, the second fired rule, if I 1 is near and I 2 is medium, then the output is low. Similarly, you can also read the third rule and the fourth fired rule. Now, actually what you will have to do is, so you will have to find out the firing strength of each of these particular rules, and that firing strength we have already determined in as output of the layer 3. And once you know this particular firing strength, now we are in a position to find out like what should be the fuzzified output for each of the fired rules. For example, say if we concentrate on the first fired rule, that is your NR SM low, that is if I 1 is NR and I 2 is SM, then the output is low. So, I will be getting the fuzzified output is nothing but, so this particular the shaded portion, and its corresponding area and center of area we can find out, and how to determine those things we have discussed in much more details. The second fired rule, if I 1 is near and I 2 is M, then the output is low, and this particular area is nothing but is the fuzzified output. I can find out the area, we can find out the center of area. Then the third fired rule, if I 1 is far and I 2 is small, then the output is high. So, I will be getting like this as the fuzzified output, the shaded portion. I can find out its area and center of area. Similarly, corresponding to the fourth fired rule, if I 1 is far and I 2 is medium, the output is your high. So, we can find out like what should be your, so this particular the fuzzified output. And once you have got this particular fuzzified output, now actually we carry out the OR operation. So, just to superimpose all such fuzzified output, and if you superimpose all such fuzzified output, so you will be getting actually, so this type of combined fuzzified output. So, this is nothing but the combined fuzzified output, and once you have got this particular combined fuzzified output, we can use the center of sums method for defuzzification, and we can find out, so this particular your the crisp output. Now, this is the way actually we determine actually the crisp output for a set of input parameters. That means, on layer 5 we carry out, so this type of your defuzzification using the center of sums method, and this 501 is nothing but the output of the first neuron lying on the fifth layer, and that is nothing but A1 F1 plus A2 F2 plus A3 F3 plus A4 F4 divided by A1 plus A2 plus A3 plus A4. So, you will be getting this as the crisp output. Now, if this is the crisp output, so this particular crisp output can be used just to find out the deviation by comparing with your the target value, that is 9.0. So, we compare, so this calculated value with the target value and we try to find out, so this particular the deviation. Now, this deviation could be either the positive value or negative value, but here fortunately we are getting the positive value, but it could be negative also, and that is why it is better to find out actually the mod value of the difference between your TO1 and that is nothing but 501. So, we can find out, so the mod value of this particular the deviation. Now, based on this particular mod value, so what we do is, so this error we will have to propagate it back for your the further modification of the network. So, we can use the back propagation algorithm for its training or the tuning, but the transfer function ought to be defined in a very nice way, so that we can carry out the differentiation at least in the logical sense, and we can implement this particular BP algorithm. So, just to modify the connecting weights or other design variables of this particular the network. Now, we can also use actually a genetic algorithm or any other nature inspired optimization algorithm. Now, if I use the genetic algorithm, so all the design variables we can keep it inside that particular the GA string. The GA will try to find out or try to evolve one optimal the Neuro-Fuzzy system, and if you use genetic algorithm just to evolve that optimal Neuro-Fuzzy system, so that will be known as actually your genetic Neuro-Fuzzy system. So, genetic Neuro-Fuzzy system is this. So, that means we are using the genetic algorithm just to evolve the Neuro-Fuzzy system, that is nothing but the genetic Neuro-Fuzzy system. So, this is the way actually we can combine this your fuzzy logic and neural network, particularly this Mamdani approach, and we can design and develop the optimal fuzzy reasoning tool based on the Mamdani approach, and this particular the fuzzy reasoning tool has been implemented using the structure of a network, and this structure we can utilize for further tuning, training, and ultimately we are going to train that Mamdani approach of fuzzy reasoning tool. Now, this is the way actually we can develop the Neuro-Fuzzy system. Thank you.